the last section, we started talking about operations between sets, like unions and intersections. And we can extend the idea of these operations to more than two sets. For instance, if you wanted to talk about the union of sets A, B, and C, this is just a set of all x in our universe such that x is an element of A, or an element of B, or an element of C. Similarly, the intersection of three sets would be the set of all x that are in A and B and C. And if we wanted to draw a Venn diagram, we could. I don't know why the box disappeared here, but here's our universe. This would be the shaded region for A union B union C, and this would be the shaded region for A intersect B intersect C. But if we added a fourth set to this, if we extended this to more than three sets, the Venn diagram is going to get awful because we'd have to find some way to add in a fourth set that intersected with each one of these existing areas, including the ones in the middle, and it ends up being, frankly, a little bit terrible. So we don't really use Venn diagrams to help us after that. And in fact, we developed a language to help talk about unions and intersections of multiple sets. So let's say we have some collection of sets. We'll call them A1, A2 through AN. So these are just a whole bunch of sets. We have n many different sets here. Then we use this notation, union, where I goes from 1 to n of the set AI, to mean, all right, well, if you've seen notation similar to this before with like a large capital sigma, it's summation notation. This is just sort of the same idea but for unions. So it just means the first set, so start with I equals 1, that would give you A1. Union, now go up to the next natural number, that would be 2, so then A2, and then keep going until you get to n. So this is just a union of all the sets from A1 to AN, and so this is going to be equal to the set of all x in our universe such that x is an element of A1, or x is an element of A2, or, right, you have to keep going down the line until we get to the last case where x is an element of AN. Another way of saying this is going to be the set of all x such that x has to be an element, right? If x is in this union, it has to be an element of one of these AI sets. So we could say the set of all x such that for some I, or there exists an I between 1 and n, such that x is an element of AI. So this is just sort of a more set theoretic notation, or using our notation from logic to say there's some index I so that that element x is in the set AI. And we can generalize this to intersections of many sets. So the intersection of AI, where I is going from 1 to n, would be A1 intersect A2 intersect all the way up to AN. So this would be the set of all x in our universe such that x is an element of A1 and, right, intersection means and, x is an element of A2, and keep going down the line until you get to the last one, x is an element of AN. And so we could write this as this x such that now it's not just that there exists one set that x belongs to. To be in the intersection, x has to be in every single one of these. So this is a universal statement. For all I between 1 and n, we have that x is an element of AI. All right, so this is a lot of kind of complicated notation. Let's do an example to make sure we understand how this works. So let's define AI for some small value of I as follows. So we're going to say A1 is the set consisting of the elements 1, 2, and 3. A2 is the set consisting of the elements 2, 3, and 4. A3 is a set with 3, 4, and 5, etc. So in general, we can define AI to be the set consisting of element I plus 1, element I plus 2. And so we're saying that I, the index, can go anywhere between 1 and 15. So I'm describing 15 different sets here. So let's do an example. The union of AI, where I is ranging from 1 to 5, is going to mean start at 1, so A1, union A2, union A3, union A4, union A5. So this is going to be one big set where we've unioned together A1. I'm just going to do a little shorthand on top. This isn't great notation. I'm just going to write here what elements are in each set. So 1, 2, and 3 are in the first set. 2, 3, and 4 are in the second set. 3, 4, 5 are in the next set. 4, 5, 6 are going to be in the next set. And finally 5, 6, 7 are in the last set. And because we're unioning them together, I'm just collecting them all up into one big set, and I end up with all the numbers from 1 to 7. All right, that's what I get for this union. Now, what if I wanted to do the intersection? It's the same 5 sets because our index is starting at 1 and going up to 5, but this time we're intersecting all these sets. All right, so we've got the same sets, right? 1, 2, 3 are my elements of the first set, 2, 3, 4 for the second set, etc. So the intersection is going to be the set of all x that are in every single one of these sets. So which elements appear in every single set? None of them, right? Because, for instance, these two sets here have no elements in common. So there's no possible way that this intersection could have any elements at all, which means this intersection is empty. But if we only had our index going from 1 to 3, if we were only intersecting A1, intersect A2, intersect A3, this we can do. Because we have 1, 2, 3 in the first set, we've got 2, 3, 4 in the second set, and 3, 4, 5 in the last set. So now there is an element that appears in every single set, namely the number 3. Okay, so we have some practice with dealing with these index collections of sets. For finite sets and for a finite collection of them, let's make this just a little more complicated. So what if we didn't have finitely many sets? What if we had infinitely many sets and we wanted to collect them all up in some way? So we say that for a non-empty index set, that a set Sn, that there is a set Sn for every n in the index set. So essentially we have this collection of a whole bunch of sets, and this I is just telling you what are the indexes. Is it S1, S2, S3, S4, S5? Or is it S1 through S15? Or is it infinitely many? Right? And so just like before, we can say that the union of all these Sn sets for every n in the index set would be the set of all x's such that x exists in at least one of those Sn sets. And the intersection would be the set of all x such that x exists in every single one of those Sn sets. All right, so we will do an example. Instead of Sn, I'm going to call my sets An, and I've defined An to be the set containing n plus 1, and n plus 2. Okay, these are the same sets we talked about in the last example, right? So A1 would be the set containing 1, 2, 3. A2 would be the set containing 2, 3, 4, etc. It's just that now, instead of only having 15 possible sets, we've got infinitely many. Now this says if we set the index set equal to 2, 4, and 6, this is saying we're only going to consider the sets A sub 2, A sub 4, and A sub 6. So the union of AI over, oh sorry, this should say AN really, because I used n here. So the union of AN, where n is in our index set, would be A sub 2, union A sub 4, union A sub 6. Okay, so that would be the set 2, 3, 4, union the set 4, 5, 6, union the set 6, 7, 8. So this would be the set 2, 3, 4, 5, 6, 7, and 8. And similarly, the intersection of AN, where n is in this index set, would be A2 intersect A4 intersect A6, which it's the same 3 sets as up here, but now they're being intersected. So 2, 3, 4, intersect 4, 5, 6, intersect 6, 7, 8. And again, there's no elements that appear in all 3 of these sets, so that intersection is empty. So again, we've only looked at finitely many sets, but we can extend this idea to look at unioning together or intersecting together infinitely many sets. So let's do an example where we're using the same AI sets as before. So A1 is the set 1, 2, 3. A2 is the set 2, 3, 4. etc. But now we're saying our index set is all natural numbers. Oh, I used the wrong index again. Okay, so our intersection of AI's, where I is in our index set, right now our index set is the natural numbers. So this is basically going to be A1, union A2, union A3, union A4. Infinitely many, right? Because we have an AI set for every single natural number I. So we need to union them all together. Oh, what have I done? I've switched the order. This isn't unions, this is intersections. Ridiculous. Okay, we're intersecting together infinitely many. All right, so this is the set 1, 2, 3, intersected with the set 2, 3, 4, intersected with the set 3, 4, 5, intersected with the set 4, 5, 6. I've run out of space, but we have to keep going infinitely many. So the question is, what number appears in every single one of these sets? And hopefully you can see that the answer is none. There is no single element that's going to appear in every set, which means this intersection is empty. How do we justify this? Let me just put a little star here. We justify this because we can find two sets with nothing in common. For instance, since A1 and A4 have no elements in common, there's no way that you could find an element that's in every single set, because already you can't even find an element that's in these two sets. So the infinite intersection is also empty. Okay. Now, on the other hand, if we wanted to union together all of these infinitely many AI sets, A1 union A2, union A3, which is what I thought we were doing the first time, infinitely many, this would be the set 1, 2, 3, union with the set 2, 3, 4, union with 3, 4, 5, and we're just going to keep doing this forever. So what are we going to get here? Well, 1's going to be in the union, because union means just collect them all up. Everybody's invited. 1, 2 is going to be there, 3 is going to be there, 4 is going to be there because it's in the next set, then 5, then 6, forever. Okay, well, what set is this? We've seen this set before. This is a set of natural numbers. Now, how do we know that that's true? I mean, it looks like it's true. The way I wrote it, this is usually how we describe the set of natural numbers, but how do we really know that it's true? To really justify this, we need some background on how do we show sets are equal in general. And so the way that we show it is, in general, if you want to show that two sets A and B are equal, that A is equal to B, you need to show that A is a subset of B and that B is a subset of A. And in the next section, we're going to spend a lot of time looking at some smaller examples so that we can build up to more complicated things like this. One other thing to note is that you might see in the exercises some examples of indexed collections of sets where the sets themselves are not necessarily going to be finite sets anymore. Like we use this AI set I plus 1, I plus 2 for all of our examples. But your index collection of sets doesn't have to be these sets. You could have an index collection of sets, let's say something like define bi to be the interval on the real number line from 0 to I, where I is a natural number. So in this case, your sets would be, you'd have the set B1 is the interval from 0 to 1, B2 is the interval from 0 to 2, B3 is the interval from 0 to 3, etc. These are not finite sets. These are actual intervals of the real number line. We're talking about all numbers between 0 and 1. This is an infinite set here. There's infinitely many numbers between 0 and 1. And similarly, infinitely many numbers between 0 and 2, etc. Okay, so just keep that in mind if it pops up. These sets themselves don't necessarily have to be finite sets. They can be intervals of real numbers, in which case the sets are infinite.